Happy New Year, all of you. So, welcome to the class for wave optics. And you do remember that, where is the duster? You had done some parts of ray optics. Actually, we won't be getting a lot of time. I just have today's lecture and some part of tomorrow's lecture to finish wave optics completely. And tomorrow I'll be taking up optical instruments as well. Okay. So till only 2 lectures I have to finish whatever the portion of wave optics is left. Okay. Any part of optics basically. So let's start. See, a little issue with the today's lecture would be that we would be a little rushed. Okay, we would rush through all the concepts. I will explain the basics. I will not be doing all the calculations. I'll be skipping some portions. Okay, because I have to finish at least interference today, so that I can take up diffraction and polarization tomorrow and optical instruments tomorrow, right? So I hope it's okay. The pace is okay. So if you find any, if you find it uncomfortable, if you find it a little quick, you need to actually go back to your basic, the NCERT books. Okay, everything, the basics are given there. I won't be skipping the advanced concepts, but I would still skip few steps from the basics, right? So, interference from wave optics. First of all, you studied the first topic, Huygens principle, right? So I'll just discuss it in brief. See now, this guy Huygens was born in some town of France, and it was called the canal town. Actually, he had so many canals. He saw so many canals while growing actually older. So the thing is that actually he had a great affinity for water waves, right? You know water waves. When in a pond, when we throw a stone, so circles travel outward, right? So he had a great affinity for this kind of thing. Okay, so the wave theory, his wave theory is actually nothing but whatever is followed by water waves, right? So one simple way to explain it is, let's say you build a wall. I'm showing it from the top view, right? You build a wall and waves are coming like this in this direction. You are at a seashore, okay? Okay, waves are coming in like this. You have built a wall, okay? Only a small portion is here, okay? What happens? The waves were straight, okay? You can see it. They were almost straight, but when the water comes out, it comes out in the form of circles. It can be imagined very easily. It's a household experiment. Okay, and you can throw a bucket of water on floor with this kind of arrangement. Some few bricks placed in such a manner so that there is no space except for this one. So from the empty space, the waves come out in this manner. So from this logic, he actually derived what? That whenever a source produces some waves, okay, let's say it produced these waves, every point on the wavefront. What is a wavefront, we say, by the way? Yeah, it is the locus of all points which are oscillating in the same phase. So he got this concept from water waves. Okay, in a canal or a pond, you can see whenever you throw a stone, the circles they spread out. So any circle is actually a wavefront, right? Because all the points on any circle are either on crest or on trough. So we actually see only the crest or the trough circles, but there can be so many infinite number of circles. You know, a circle slightly larger than the crest is also a wavefront because it has all the points which are in the same phase, right? So this kind of arrangement, wavefront. Now he said that every point behaves like a secondary source. It means what? That it produces waves as if it has all the energy to produce the waves. It has no knowledge of whether the waves are coming from rear, or whether the waves are produced by itself. So this point behaves as if it is producing the waves. It starts producing like this, it starts producing like this, and so on. The next wavefront is like this, the tangent curve, or we call it envelope. Okay, envelope to all the small wavefronts, okay, or wavelets we call it. Okay, so the shape of wavefront is like this. It grows in this manner. Direction of motion of wave is always perpendicular. This is what he said, right? Okay, so you understand a lot of this. I would just be asking one or two questions. You already know this is point source. It produces spherical wavefronts. A line source would produce what? Cylindrical wavefronts. And a plane, which means like a sheet, it would produce planar wavefront, a sheet of light. Okay, so actually one thing you should know also, that these spherical wavefronts at very large distance, the radius of sphere becomes very large, which means that they would appear like plane wavefront. Okay, so that's why sun is a spherical source. Nearby sun, the wavefronts are spherical in nature, but when they reach here, we consider sun as a source of plane wavefront, right? Because the distance is large, the radius of wavefront would be equal to the distance between sun and earth, huge distance, right? So wavefront would be plane for our purpose, right? So spherical and cylindrical wavefronts, they become planar when the distance is large. Is it okay? Okay. So it's not every time when you need a planar wavefront, you need to have some sheet kind of source. Not needed. Okay. Just place a point source at a very large distance. It will do. So the concept I wanted to ask, whether you understand this. A very simple question. Okay, you have this kind of light, a lens, okay, and what happens here? This is the focus. This is the point where light would meet. So can you tell me what kind of wavefronts would be there on this side and on this side? If you could just draw the wavefronts. This thing would happen. Wavefront here would be perpendicular. Just you need to understand this, that wavefront is always perpendicular to wave direction. Here wavefront would be shaped like this. Why? Because always perpendicular to wave direction. So for convenience, you can draw a small portion of wavefront here, small portion here, small portion here, join them by a smooth curve, right? Okay. So you can draw wavefronts in any kind of situation. I am not going to explain it any further. Just do remember this kind of arrangement. A plane wavefront, when passes through a small slit, becomes cylindrical, or if it is a point pinhole, so it becomes spherical, right? Is it okay? This forms the basis of diffraction actually. This forms the basis of diffraction, but that we will study later. Now let's start with interference. Now, you already know a few basics of interference. Interference means what? This source S1 and this source S2, they are producing some wave which overlap at some point. Okay, so at this point, the intensity, not intensity exactly, let's first discuss the displacement. At this point, the displacement of resultant wave is actually vector sum of the displacement between two waves. And what happens? The intensity is not always sum of the intensities due to two waves. Do you remember what is intensity? Intensity, do you remember? Power upon area. Okay. Last year in third dynamics there was a term intensity, or you call it emissive power. Emissive power is nothing but intensity actually. So intensity is that. Okay. So it is not equal always. It is not like that it would always be unequal. There may be some cases where intensity is actually sum of the two intensities due to individual waves, but it is not always true. Intensity may or may not be equal to the sum of intensities. And if we consider the logic, actually what is happening? If intensity, if some energy from wave 1 is coming and some from wave 2 is coming, what should happen actually? Total energy should add up, but it's not happening here. Okay? So a redistribution of energy happens in this region. Okay? Some portions get more energy than the sum, some portions get less energy than the sum. This phenomena is called interference. Okay, so what is interference? Interference is the, this is just very crude form actually. We study a very refined kind of form in Young's double slit experiment. So interference is what? The superposition or overlapping of two waves which have same frequency, first of all, okay, and which travel in same or almost same direction. Okay. Also, one more thing I should also mention, there should be a constant phase difference as well. Okay, we would discuss this when we study coherent sources here. Okay, why constant phase difference is necessary. Okay, so in this wave 1 is y1 a1 sin omega t. Actually, if you remember from 11th, the wave equation is actually this. Omega t minus kx. We ignore this portion. The reason for that is that for both the waves, since they are traveling in almost same direction or same direction, x would be same. Okay. K is what? 2 pi by lambda, the angular wave number. Okay. K is the angular wave number. So if frequency is same, wavelength would also be same. Light ki wavelength, frequency is same, wavelength would also be same because speed is also same. Both the waves are traveling in same portion. So that's why we ignore the minus kx term, because it is same for both. Is it okay? It is same for both the waves. So for wave 2, we assume that there is a phase difference phi. Now phase difference phi comes, all this interference is actually, whatever concern us is actually just the calculation of phase difference or path difference. Okay. If we study, phase difference or path difference, everything is done. Okay. So now this comes when one wave has to travel more distance as compared to other, or one wave passes through some other medium because of some issue. Okay, some disturbance in the medium or something else, right? So we will discuss these things. Now, if this is the arrangement, the total wavelength, the total displacement would be this. And I can spread it sin omega t cos phi and cos omega t sin phi, right? We can always, combine these two terms and these 2 would become A2 sine phi cos omega t. Okay, I can go on like this. Frankly, taking this as r cos delta, taking this as r sin delta, you can calculate whole of this. I'll just write the resultant directly. Okay, you already know this. This is not something which should be discussed here. Pre-boards are going on, so you must have studied this. So this is a1 square plus a2 square plus 2a1 a2 cos phi. Okay, this is the resultant amplitude. Okay, now for our convenience, wave 1 is like a phasor. If you remember the AC class, okay, we represented AC current and voltage as phasors. I am representing the wave also as a phasor. Okay, so wave 1 is represented by a phasor of length a1. Wave 2 is represented by a phasor of length a2, but at an angle phi. Okay, so the resultant now would be this. R, and this is the angle delta, the phase angle of the resultant wave, right? So R is this, and if you find tan delta, it would be nothing but this height upon total base. Okay, it is exactly like vectors a2 cos phi upon a1 plus a2 sin phi, right? Okay, so instead of going all the way like this, please use phasor notation for your exams. Okay, even for school exams you can use it whenever you don't need to prove anything. For numericals you can use it directly, right? Okay, so the final wave would become r sine omega t plus delta. This is the final wave. Okay, now let's have a condition. If a1 and a2 both are equal, see, we deliberately try to have intensities of two sources equal. Okay, it gives us better contrast. We'll study this in YDSC, that how it gives better contrast. So when amplitudes are equal, the resultant would become how much? Under root a square plus 2a square cos phi. So this is under root 2a square 1 plus cos phi. And you already know 1 plus cos phi is 2 cos square phi by 2. So this is directly written like this. ठीक है? Okay, a can come out यहाँ से, you can use this. Two a square into 2 cos square phi by 2, which actually becomes this. Okay, so can I erase this? I guess it's all done. And from here you can see the resultant, maximum value of resultant is 2a. Okay, and the minimum value of resultant can be 0. Resultant amplitude I'm saying, okay, this is the resultant amplitude. Amplitude of a wave can never be negative. Okay, amplitude defines the size a wave would take. So size of a wave, which means size of crest, can never be negative. It can be 0, right? So if we have both the waves of same amplitude, what happens? Minimum becomes 0. So here no light condition, and here twice amplitude. What it would mean, we will just understand. For intensity, you already know, if you remember the last year's wave, and even if you don't, doesn't matter. Intensity for a wave is actually proportional, we say. Even for sound waves, it is proportional. Okay? Even for sound waves, it is proportional. So, okay. So it is Ka square. There are other factors as well, the medium features and all. They come that all those factors, they are they compromise K. They form K. All the factors, the medium, the nature of medium thing, and the wavelength and all. Is it okay? So except for amplitude, I include everything in K. I am assuming that it is a constant because both the waves have same frequency and they move in the same medium, right? So I is Ka square exactly. Okay. So now I1 can be written as Ka1 square, which means A1 is under root I1 by K, right? And A2 is under root I2 by K on the same lines. So the resultant was this A1 square plus A2 square plus 2A1 A2 cos phi. Okay, let's take resultant as under root I by K, where I is the final intensity, resultant intensity IR. Okay, IR is the resultant intensity. So now replacing, what you get? Under root IR by K is under root I1 by K plus I2 by K plus 2 root I1 by K root I2 by K cos phi. K cancel from all these. If you square it, resultant intensity is I1 plus I2 plus 2 root I1 I2 cos phi, right? Okay. Am I going too fast? ठीक है, okay, workable. So the resultant intensity now becomes this. Okay. And for this kind of scenario, you can understand maximum intensity would become 4Ka square. The minimum intensity would become 0. Initial intensity was Ka square, right? I1 and I2 would be equal, na, because amplitudes are equal, right? Amplitudes are equal, so intensity would be equal. So if I1, I2 both are Ka square, this would become 4 times individual intensity. So at any point, I1 intensity is coming, I intensity is coming, and from another wave, I intensity is again coming. Total should be 2A, but here we are getting 4 times. Okay, so what happens? The intensity coming to this portion, it should also be 2 I1, right? This is transferred to this portion. Energy from all minimum portions is transferred to the maximum portions, right? This is called redistribution of energy, and that's how we say that actually energy is still conserved, right? Total energy is still same because we are taking energy from one portion and giving it to another portion. So one portion becomes a lot bright and other one becomes totally dark, right? Okay. So this was basic for interference. We haven't discussed the YDSC. What would happen actually? Apart from the regular YDSC which we have studied, we would study a lot more other things. Okay, in YDSC, a lot more variations which had been a part of JE. Okay, which had been introduced in JE in the past years. And all of this interference, it depends on what? Formation of two sources, right? Interference is a game of just two sources which produce wave of same frequency or coherent waves. So we would discuss coherence on this matter, okay? And we would discuss a few more ways in which we can produce two different waves, coherent waves, right? Which can interfere, okay? So can I erase this? Acha, one more thing I missed actually, sorry. I'll write here. The maximum intensity was this one, right? I1 plus I2 plus 2 root I1 I2 cos phi. Okay. Now for maximum means bright portion, cos phi should be 1. I would become I1 plus I2 plus 2 root I1 I2. Right? For minima, you already know, cos phi should become minus 1. So I would become I1 plus I2 minus 2 root I1 I2. Now if you consider this is actually nothing but root I1 plus root I2 whole square. If you consider this is root I1 minus root I2 whole square. Take ratio. Okay. Maxima, ratio of maximum and minimum intensities is this only. Okay. Now if they are equal, the denominator becomes 0. Okay. The ratio becomes infinite, right? The upper one would become 4i and the lower one would become 0, right? So let's have a few questions on this basic thing. Now let's start. I'll erase this, okay? Now check. So we just discussed the theory of interference, basically intensity, right? Now question says this: we have two waves. The first one is 3 sine 100 pi t, and the second one says 4 sine 100 pi t plus pi by 3. Okay, you can see that actually their wavelength is equal. Okay, this term, whole of this is omega actually, which is nothing but 2 pi f. Okay, 2 pi into frequency. So frequency would be 50 hertz, right, for both. What is given? The intensity of first wave is I1, I naught. Okay, first intensity of first wave is I naught. You have to find resultant intensity. Okay, you have to find resultant intensity. The intensity of second wave is not given, but you can still calculate it. Okay, you can calculate it because I naught can be written as k into 3 square. So you can write I2 as k into 4 square. Okay, and you can write I2 in terms of I1, right? So please solve. I don't know how many students are online right now, but if there are any, please actually you also try to solve. Hmm? 37 is the resultant intensity. 37 I naught by 9 may be a correct answer. Let's check. Now see, you know I1 by I2, the ratio would be A1 square by A2 square. Okay, right? So you can see that this is I naught, this is I2. I1 is given as I naught. Okay. This is 3 square, this is 4 square. Yani 9 by 16. So I2 would be 16 by 9 I naught. Okay. The intensity, final intensity, sorry, is I1 plus I2 plus 2 root I1 I2 cos phi. You can use it. Intensity I1 would be I naught, I2 would be 16 by 9 I naught, and 2 root I naught into 16 by 9 I naught. And cos pi by 3 is half. So it would cancel. So I naught plus 16 by 9 I naught plus 4 by 3 I naught. Okay, these two would come out of root. Okay, so you can take LCM. Answer would be how much? 37 by 9 I naught. Okay. Another easier question. Another easier question. I hope I can erase this one. This is easy. The easier question is this. Actually, what happens? Two waves. Wave 1 has intensity I, wave 2 has intensity 4I. Okay, they interfere. You have to find the ratio for this. It's a very easy question. Okay, ratio of maximum to minimum intensity, very easy question. I hope it can be done directly. Answer is 9:1. Do I need to solve? नहीं हो जाएगा ये तो है ना. Now I'll erase this. Okay. Now let's discuss YDSC. Okay, Young's double slit experiment. What he did, actually initially what he did, he took a cardboard, okay, allowed light, well, he made a pinhole in a cardboard. So in that pinhole, from that pinhole he allowed light to enter into a dark room. He placed a cardboard with two pinholes, okay. So initially there was one cardboard with one pinhole, then two pinholes, and then there was a screen, okay. All were quite far off, okay. So the purpose was, the distance here was large to make the wavefront plane, you remember it, okay. And from here the waves would come out like this, so they would spread everywhere like this. What happens on this screen? On this screen, the waves from two different pinholes, they interfere, right? They interfere, and a pattern of, ideally what should happen, one bright spot here and one bright spot here should be seen, but actually there is a beautiful pattern, bright and dark kind of pattern seen. So from this actually he confirmed that light is a wave, right? So he modified this. This was Young's pinhole experiment, two pinhole experiment, okay. He modified this, modified the first pinhole into a slit. What is a slit? It's actually a line source. From a cardboard, let's say this is a cardboard, you are cutting this kind of arrangement, okay. This is not actually a slit actually. Slit should be very thin, something like this, okay, long but very thin, okay. So it behaves as as a line source, Okay, the wave fronts out of it would be cylindrical in nature, not spherical. Still, they would do the same kind of thing. So we would discuss that. Just wait. Now, what happened? He actually placed one slit here, allowed light to come in. Then he placed the two slits symmetrically, and here was the screen. Right? You need not draw the diagram, it's your wish actually. Don't, it would actually take time. If you want to draw, only then draw, and this would still be available on video, right? So you can anytime refer to the diagram. What happened actually, light from this, cylindrical wavefront from this came, and by the time they reached this portion, they were plane, okay? The distance was large. From this portion, two cylindrical wavefronts came. This distance was taken as capital D. The separation between slits was taken as small d. Okay? Okay. The slits and the screen were parallel. Now, this is not the only arrangement. This is what Young did. This is the experiment which Young did. And the JE people, they do a lot of experiments with the Young experiment itself. Okay? So, we would discuss what actually can be done. So, what happens actually, here is the middle line. I am drawing a line, the middle portion. On this middle portion, the waves from two slits would travel after covering equal amount of distance. Okay. Earlier also, they were coming to the slits while traveling equal distance, right? So, there was no path difference. We would discuss path difference and then discuss phase difference related to it. So, what is happening? There is no path difference here. Again, there is no path difference. So, here what would happen? The two waves coming would be like this. A sin omega t, the other one would be again A sin omega t. No phase difference. Let's discuss actually why phase difference, why discussion of path difference and phase difference is important. Okay, let's consider any point P here, which is at some distance. What happens? The wave here would travel less distance and the wave here would travel more distance. Obviously, this would travel some extra distance, which is called path difference delta x. Okay, or in some texts it is written as delta only. So suit yourself actually, whatever notation you find comfortable. What happens actually, if this path difference is 0, crest of first wave overlaps with crest of second wave. Okay, you can understand that the resultant wave would have double sized crest, which means 2a amplitude and 4i intensity, right? Now, if there is a path difference of lambda by 2, half wavelength means a difference of one crest or trough. So, if if the first wave, if the crest due to first wave falls at P point, trough due to this wave falls at that point, P point. Okay, let's see. Let's say the distance is just 3 wavelength long. For our assumption, actually it's large, but for our assumption, let's consider the distance is just 3 wavelengths long. First wave reaches after traveling this much distance. The second wave reaches after traveling 1, 2, 3, and here. No, okay. Okay. So, for second wave crest and for first wave trough, they match. What happens? Resultant displacement would be 0. Okay. If the amplitudes are equal, it would be 0. If they are not equal, it would be non-zero, but small, right? So, whenever the path difference has a factor of lambda by 2, what happens? A destructive interference or a dark fringe comes in picture. Is it okay? I hope it is clear. You know, for small we just discussed, let's say the distance is lambda, just 3 lambda, sorry. Okay. So for from first wave 3 waves would come, but from the second one, since it is traveling larger distance, 3.5 waves would come, and a half wave can make or break your situation, right? Okay, right here. Okay, so this half wave actually causes opposite displacement for the second wave, which causes resultant 0. Okay. Okay. Now let's discuss it from our wave point of view. You remember that actually we considered wave 1 as a sin omega t. Okay. In one wavelength, do you remember? In one wavelength, a wave covers 2 pi phase. What it means? What it means? If you remember, you know, water waves or rope wave. Okay, you can create by shaking a rope. You can create waves. Okay. In one wavelength, what happens? Any particle of the rope goes to the crest, then comes down, goes to the trough, and then comes back. It completes one cycle. One SHM cycle is complete, right? One SHM cycle means 2 pi phase covered. Okay, if you remember the last year's class, 2 pi phase is covered in one SHM cycle. So whenever one wavelength passes, one cycle of SHM is covered and 2 pi phase is covered, right? So here we can see if lambda is the path difference, then phase difference would be 2 pi. If 1 is the path difference, phase difference would be 2 pi by lambda, and if delta x is the path difference, phase difference is 2 pi by lambda into delta x, right? Okay, so whatever is the path difference decides what kind of brightness would be there in the situation, right? And calculation of delta x is the only important step in YDSC or in any form of modified YDSC. You need to identify delta x every time. It is just that. Okay. So for here, for this central portion, what happens? Both the waves cover same distance, so delta x 0, phase difference 0. Okay, constructive, happy sub. Slightly above, what happens? The wave from first slit travels less distance, the wave from second one would travel more. So if this is the point where delta, I will draw this. This is the point where delta is 0, intensity is 4I0. This is the point where delta is lambda by 2, intensity would be 0. Hoga na? As you go up, path difference increases. Slightly above, the path difference would be how much? Lambda. When lambda is the path difference, you can check phase difference would be 2 pi. For 2 pi, cos phi is again 1. Cos phi 1 matlab constructive फिर से, right? We discussed it. Cos phi 1 means bright and cos phi minus 1 means dark. Okay. For lambda by 2, you can check 2 pi by lambda into lambda by 2. It is pi. Phi is pi. For this one, it is pi. Okay. For lambda by 2, the phase difference is pi, and so it is destructive interference. Next, again constructive, I is 4I0, and so on. So what happens? This kind of arrangement happens. This is the dark fringe. Again, at some distance, again a dark fringe. Again, at some distance, a dark fringe. Okay. The center would be bright, and okay, the ordering starts like this. This is called the central bright fringe or zeroth. This is first dark, this is first bright, then second dark, then second bright, and so on. On the lower side as well, first dark, first bright, second dark, second bright. Okay, okay. So let's try to find the general condition actually. Okay. Let's try to find the general condition and the position of fringes. So can I erase this? This is actually what happens in the real world. experiment, and we would be drawing a 2D image of this. Okay, can I erase this? Okay, the position of point P is y. Is it okay? So from the middle I draw this line, and let's take this angle as theta. If the distance is large as compared to the distance between slits, okay, you already know this is the condition. Okay, what happens? This is theta. This angle will be slightly more than theta, and this angle will be slightly less than theta. We can take all three of them as theta. Okay. Now drop a perpendicular. Basically, take this as center, and the smaller distance as radius. Draw an arc. The arc would be like this. So if this distance is some x, even this is x, the remaining distance is your path difference delta x. Let's try to find that. If this angle is theta, this angle is how much? 90 minus theta, and the angle there is theta again. So I am talking of this kind of triangle. This is theta, this is d. Here are the two waves which were going. Okay, I am separating this here. The angle here was theta, this one. Okay, so if this is d, this is what? The perpendicular. Perpendicular would be d sine theta. Okay, right? So this is d sine theta. So very simply we have found the path difference to be d sine theta. Straightforward. Now we already know that the distance is large, the angle would be small. If the angle is not small, then we have to stop here, right here. Okay. If the angle is small, then we can write sine theta as almost equal to tan theta, which for this triangle would be y upon capital D. This is a big triangle, right? Y upon capital D. So I can write path difference as d tan theta or dy by capital D, right? Okay. Okay. So it's a game of two triangles. One triangle is here to calculate the path difference. One triangle is here to calculate tan theta, right? Okay. Now on the basis of the discussion we did earlier, can I write phase difference as 2 pi by lambda into delta x? Okay, है ना? So for constructive, from here, let's split it into two parts. 2 pi by lambda into delta x. Here one part, here one part. For constructive, what happens? For constructive, 2 pi by lambda phase actually difference should be how much? You already know for constructive cos phi was 1, and if you remember the trigonometrical equations in maths, right? If you remember that, phi should be equal to 2n pi. Okay. General solution is this. When n is 0, it is obviously 1. Phi is 0, n is 1. Phi is 0, cos phi is 1. Phi n is 1, then cos phi would be again 1. This would be 2 pi. If n is 2, this would be 4 pi, again 1, and so on, right? Okay, so phi is this thing. So 2 pi by lambda into delta x is equal to 2n pi. Cancel this thing. Delta x will be n lambda. So when path difference is n lambda, we get constructive. Okay. Okay. Now delta x equating from this equation, dy by capital D is n lambda, and you get y is equal to n lambda capital D by small d. Okay, this is the condition. This is the position of nth bright fringe, right? This is for bright fringe. For dark, for destructive, cos phi we remember was -1. Okay, which means phi should be equal to 2n pi plus pi, can I write? Or minus pi can I write? I would prefer minus. I'll explain in a little while. Okay, this can be written as 2n minus 1 pi, right? So going by this logic, 2 pi by lambda into delta x is equal to 2n minus 1 into pi, and delta x would become 2n minus 1 into lambda by 2. So this is even multiple of lambda by 2. I can write it as, obviously write it as 2n lambda by 2, right? Even multiple of lambda by 2. This is odd multiple of lambda by 2, and here you get dy by capital D is equal to 2n minus 1 lambda by 2, or you get y is equal to 2n minus 1 lambda capital D by 2d. Okay. This is for dark fringe. Okay, this is the position of dark fringe. You can find the fringe width. Fringe width is the distance between two consecutive bright fringe or dark fringe, right? Two consecutive bright fringe or dark fringe. So these are the things that you already know. So fringe width I'll also write, bus. Fringe width beta is yn plus 1 minus yn. Nth bright fringe, position of nth bright fringe minus nth, position of n plus 1th bright fringe minus position of nth bright fringe. Okay, this can be y2 minus y1, y3 minus y2, and so on. You can obviously calculate this would be lambda capital D by small d. Even for dark one it is same. Okay, the separation between two dark fringes, two consecutive dark fringes, is still the same. Okay, so now from here onwards let's discuss something different now. Okay, these are the trivialities which you already know. I just wanted to recap it, right? Can I erase this? इतना आता था या नहीं आता था? आता था. कुछ tits and bits missing होंगे. What we want to learn from here is that delta x 2n lambda by 2, this is the condition for bright, and delta x is equal to 2n minus 1 lambda by 2, this is the condition for dark. Why was I naming it in this manner, in this fashion? When n is 0, do you know I ordered it in this manner? The central was called 0th, है ना? So this was the central one. N equal to 0 put करना है यहाँ पे. You get delta x is equal to 0. Okay, position also as 0. For first put n1. Now dark fringes don't start from 0, they start from 1. So put 1 here. You would get lambda capital D by 2d. So that's why I used -1. If I had used plus sign here, you would have got the position as 3 lambda capital D by 2d. You would have missed 1. Okay. Okay. So to keep the naming on the screen and in the formula same, I introduced -1 here instead of +1. अगर +1 करना होता, I would have used what? If I have used +1 here, then I would have to use the counting from 0. Okay, जैसे यहाँ पे 0 से counting शुरू किया, I would have to start counting from 0 here also. But 0th dark fringe, it doesn't exist. Okay, just a second. Okay, now where is the duster? Here it is. Now let's discuss very simple case. You might have studied it. let's discuss a very simple case, situation in which two waves are simultaneously, two patterns are simultaneously formed, which means that actually in Young's double slit setup, you are passing lambda 1 and lambda 2, okay, which means light from here includes both these wavelengths. You already know that both these wavelengths will form their independent pattern. This is, let's call the topic as YDSC with two wavelengths. Okay, YDSC with two wavelengths. At a center, what happens? Bright fringe for both wavelengths, because at center path difference due to both would be 0. At center path difference due to lambda 1 and lambda 2 both would be 0. Center पे सबके bright बनते हैं. Okay, the issue comes when you discuss things about first dark, first bright and so on. Why? Because if you do remember, the fringe width was this. It was dependent on wavelength. So bigger wavelength would have wider fringes and smaller wavelength would have narrow fringes. So by the time first dark fringe of bigger wavelength comes in, maybe three bright fringes of narrow wavelength would have passed. Okay, so the pattern would be a mashup of the two interference patterns. Okay, so at Y point, okay, we are discussing what happens where the two fringes will overlap, where the patterns will overlap for the next time. First they will overlap at center, and where they will overlap for the next time, let's discuss. The patterns would overlap, the bright fringes I should say, because I am discussing it as per bright fringe phenomena. The bright fringes would overlap when y n1 is equal to y n2. At the same point, let us say third bright fringe of first wavelength and seventh bright fringe of second wavelength are overlapping. Position is same, right? So y1 should be equal to y2 for the first and for the second. Position is same, positions are equal. The only problem would be ordering. What? Why? Because let's say wavelength 1 produces only 3 fringes. Okay, so n would be 3 for wavelength 1. If wavelength 2 produces 7 fringes, they would be placed like this. So they would overlap somewhere here. So for lambda 2, n would be 7. So only problem would be ordering, okay, not the position. Position would still be same. So you can write n1 lambda 1 capital D by small d is equal to n2 lambda 2 capital D by small d. Because setup is same, the separation between slits, the distance of screen is still same. So these things they cancel out. You get n1 lambda 1 is equal to n2 lambda 2. This is the condition. Okay, wherever it satisfies, you will get an overlap. Okay, we need to find where it satisfies for the first time. Okay, so n1 and n2 should be the smallest possible values at which this happens. Okay, so for example, if wavelength 1 is 3000 angstrom and wavelength 2 is 5000 angstrom, okay, these two values would be equal only when n1 is 5 and n2 is 3. Obviously they would overlap. Okay, these two conditions would satisfy. Okay, ठीक है ये चीज, the product should be equal. So you need to search for that number. It's a kind of a trial and error thing. N equal to 1 would not satisfy if you take n as 1. n2, the value of n2 would become less than 1, which is not possible because fringe, you can either have first fringe or second fringe, you cannot have 0.5 fringe, right? Okay, so first fringe or second fringe or third fringe, so you have to try out. So if I try the product of lambda 1 n1 lambda 2 n2, it comes equal. So this is the first time they would overlap. The next time they would overlap when this thing happens. The next time they would overlap when 15 and 9, then 20, and in the same order it would keep on multiplying, but the first overlap would come at this point. So if you want to find out the position of overlap, just put the value here. Okay, so let's have a question on this. Can I raise this? Now, the question says two wavelengths lambda 1 is equal to 4000 angstrom and lambda 2 is equal to 7000 angstrom produce interference patterns simultaneously. On a YDSC setup. Okay, you have to find position of first overlap after central. Okay, you can take small d as 1 mm and capital D as 2 meters. Wavelengths I have already given. Okay, and you can understand अभी तक समझ आ गया होगा. It would be 7th fringe of this one and 4th fringe of this one. They would overlap, right? Product is same. I guess you would have done it by now. So n1 lambda 1 should be equal to n2 lambda 2. This should happen. Only then there would be an overlap. We just studied it. So you can understand n1 into 4000 should be equal to n2 into 7000. Obviously the units are angstrom, so they would also cancel. Okay, so 4n1 is equal to 7n2. The numbers which satisfy this condition are 0, 0. Obviously if n1 is 0, n2 is 0, it would still satisfy 0 is equal to 0. 7, 4, right? n1 is 7, n2 is 4, 28, 28. Next one would be 14 and 8 and so on, right? So the first set is 7, 4 after central. 0, 0 means central, right? 0th fringe of this one and 0th fringe of this one would overlap. To find y, the position, you need to do what? n1 lambda 1 capital D by small d, right? Okay, this is the position. You can obviously take y2 n2 lambda 2 capital D by small d. Marzi hai. Okay, so this is 7 into 4000 into 10 raised to the power minus 10 into 2 upon 1 mm is 10 raised to the power minus 3. I won't be solving it, don't worry. So you can solve it on your own. Okay, I'll just be erasing it and moving over to the next topic. Okay, can I erase this? Okay, as I said, the class would be a little rushed. I am not giving that much time. I am just taking very few problems. Okay, I'll try to cover as many topics as possible. Okay, let's hope you solve the questions for this. Can I erase this? Right. So now the next thing would be if you submerge the setup in a liquid. Okay, if you submerge the setup in a liquid, whole of this is in a liquid, what happens now? You remember the position of bright fringe was n lambda capital D by small d. In a medium, the speed becomes c by lambda, the frequency remains unchanged. Okay, sorry, c by mu ho jana chahiye. Speed becomes c by mu. Since frequency remains unchanged, the wavelength should actually become lambda by mu. Okay, because speed reduces by mu times, so wavelength should also reduce by mu times. Since frequency is same, product should be same, right? Okay, so you can see that lambda here would then become n lambda by mu into d, lambda naught by mu. So this would be y naught by mu. Okay, if the original fringe was formed at 5 mm, after immersing in water, the new fringe would be formed at 4 by 3, 5 mm by 4 by 3 position, right? If the original fringe width was, this was lambda capital D by small d, now it would be lambda naught capital D by mu d, or beta naught by mu. So if the original fringe width was 0.1 mm, now it would be upon 4 by 3, right? Okay, now it would be lesser. So whole of this arrangement will shrink, right? पानी में भिगाने से कपड़े shrink हो जाते हैं ना, हमारा setup भी shrink हो गया, right? So dipping in water shrinks the pattern, right? Okay, okay. Can I erase this? Now we would discuss what happens when only one of the portion is dipped in water. Now that would be tricky, right? एक के साथ गड़बड़ हुआ, एक के साथ नहीं हुआ. Let's check. Can I erase this? Okay, this was just a passing kind of topic. You can say immersion of setup in water, in liquid. Okay, YDSC in liquid. You can write the name for namesake. Okay, okay. Now this is mu here, a liquid of optical density mu. Okay, optical density and refractive index are the same thing, right? Okay, can I erase this? Now slight more gadbad. Let's check what happens in our setup. What was actually happening? The source was placed symmetrically, बिल्कुल अच्छे से रखा गया था, so that यहाँ से यहाँ, from here to here, no path difference is introduced, right? What if I do this? Now there is a path difference. You obviously know this. Okay, what would happen in this kind of arrangement? So, ठीक है? So this is YDSC with unsymmetrical source position. Now from here actually we start YDSC in the proper form, like for exam purpose. Okay, before it was like a repeat of the CBSE syllabus, right? A repeat of NCRT. Now from here, now tell me what would happen? Where should the central bright fringe shift? किस तरफ जाना चाहिए? ऊपर, exactly. Because what happens, the wave here travels extra distance. Okay, so here, if this comes here and this comes here, the path difference here, which is extra, will always be there. Okay, central will not be formed here, central bright fringe will not be formed here. Slightly above this, what happens? Now the lower one has to travel more distance, है ना? The lower one has to travel more distance. Is it okay? So now extra path covered by first should be equal to extra path covered by the second one. It is offset now. Is it okay? Now let's do the analytical part. Okay. Let's say the source forms an angle theta. What happens actually? The central is formed, the central bright fringe is formed on the same line. Is it okay? At same angle theta. How? Let's check. The path difference here would be, can we find the path difference like this? Dropping a perpendicular, this much would be d sine theta. And on this side as well, the path difference is how much? D sine theta. Right? Okay? Okay? So when angle on both sides is equal, the central is formed here. I mean, like if I shift the source down through an angle 30 degree, the central bright fringe will shift to 30 degree above. Is it okay? Okay. So again, position of central bright fringe, y central, would be how much? Do you remember how we used to do it? D sine theta was the path difference. Okay. And it was actually d into y by capital D. Tan theta liya tha, sin theta was taken as tan theta, should be equal to, this was delta x. Okay. Okay. Actually, in this case, no, I would not be doing this. In this case, y should become d sine theta. This d cancels. D sine theta is the path difference here, right? On the left hand side, and on the right hand side, the path difference is, dy by capital D. Okay? 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 The sine thing is actually same on both sides. So, I mean, like, it's not that kind of a rocket science to calculate. The angle here and the angle here is same, right? So if you know the angle, you can obviously calculate the position of central fringe, right? It's just a matter of calculating the ratios, sin theta, cos theta, tan theta, right? Is it okay? Okay. So if the system gets unsymmetrical, this kind of thing happens. Can I raise this? Can I raise this? I wanted to discuss a question, but let's first discuss our topic. Now, optical path first we'll discuss. Let's say this is length L in vacuum. Okay, this is tube of length L, and this is vacuum. What happens in this length L? There would be waves like this. If a wave is passing through, the wavelengths would be like this. The number of waves, or you can say first let's calculate the time. The time of travel would be L by C. You already know this, है ना? Now you filled it with some medium, refractive index mu. What happens now? The time of travel would become L by V. L by V, right? So it would be like mu L by V, mu L by C, because you know V was C by mu already. Okay? So same distance okay, in both the cases. But for light, what is happening? Light is taking lesser time to travel, more time to travel through this distance. Okay, is it okay? It is like this is t naught, so let's call it mu t naught. Light takes mu times the time in medium. So we can do two things. I mean, like, we can imagine as if, just consider this thing, we can imagine as if the path is a little longer, the path length is mu l, but inside there is vacuum. Getting my point? Instead of having a medium, let us just increase the path length mu l, okay. The time taken here would be same, so I am drawing an equivalent diagram. समझ आ रहा है ये चीज? Okay, for light, even though for us the two lengths are equal, for light this distance is more. Why? Because its speed is reduced. Okay, just imagine that you can run like PT Usha on roads. Okay, but obviously you cannot run like PT Usha in fields where you have vegetation. Okay, so for you, while on road you can travel, you can say you can run 200 meters very quickly, but in fields this 200 will appear like very long. इतना लंबा distance था field में, it would appear like this, right? Same distance. Why? Because your speed has reduced. So effectively you would cover lot more distance. This is happening with light. The time in which it travels through this medium, in the same time it would have traveled this much distance. So instead of keeping the medium, we are now introducing increased distance. This increased distance is called optical path. This is the path which light feels that it is covering, right? Okay, optical path is the increased distance which light covers in the same time. So in water, if light covers 1 meter in vacuum, सब लोग लिख रहे हैं, write, or you can write, all of you first, right? So this thing is the optical path, and it is distance traveled by light in same time as when it travels through a medium. Okay, don't go after the definition, just simply in numerical terms understand this. If light is traveling 1 meter in water, it would have traveled 4 by 3 meters in vacuum straight away. Just multiply the refractive index, your job is done. Is it okay? Okay, so now these two paths are not same for light. This second path is longer, and if I consider the difference, the path difference, it would be mu l minus l or mu minus 1 l. Okay, this is the path difference. So for us there is no difference, right? दोनों ही L हैं. For us there is no difference. For light the path is different, right? So what happens? Light comes here earlier and it will come out of this portion later. Okay, this will cause problems for us. Let's check. Can I erase this? Okay, can I erase this? Now, YDSC with a thin slab with a slab. स्लैब समझ लेते हैं. What is happening actually? You have introduced a slab of thickness T in front of one of the sources, right? Okay, you have introduced a slab in front of one of the sources. So what happens now? Obviously at this point the two waves, it appears that they would travel the same amount of distance, but it is traveling, the wave from S1 is traveling longer distance. You already know, okay, the distance for this wave will increase. So obviously at this point the path of two waves will not be same. It will be same a little above, यहाँ पे कहीं पे होगा, where the actual path traveled by S2 is more, but because of this this medium in between, the optical path would be same. Okay, so let's have this kind of arrangement. Okay, you know, for normal calculation, if this angle is theta, the path difference is d sin theta. For normal calculation it is d sin theta or dy by capital D. Now there is a problem. Because of T thickness, what happens? The path becomes mu T. The path, extra path it has to cover, extra path is how much? Mu minus 1 into T. T तो पहले भी करता ना. If there had been no slab, then it would have to cover T in air or vacuum. Now it is covering mu T. Okay, the extra path covered in the previous also, we understood this, right? The path difference would be mu minus 1 into T. Okay, mu T is the path covered when medium is there, and when you remove it, it has to still travel through this much amount of vacuum. Is it okay? So it would travel through T distance in vacuum in that case also. So the difference is mu T. So actually the path, this portion should be equal to this extra distance traveled, so that the path, extra path for both of them is equal. Getting my point? What is happening? We are introducing, because there is path difference in the first wave, we are introducing a path difference in the second wave. Now if the path difference of two waves is same, the path would be same, right? Is it okay? So the path difference d sin theta, if I consider the total path difference, would be actually this. And this should be 0 for central. How I wrote this, I will explain it. Let me just first explain what is happening. For the lower wave, the extra path is d sin theta. For the upper wave, the extra path is mu minus 1. Okay, so the path difference would be how much? This. Okay, these two portions are equal. Do you remember? We took this as the center, we took shorter one as the radius, and we drew an arc. Construction करते थे ना बचपन में, करते थे ना, दो lines ऐसे, यहाँ पे इसको center लिया, and we are taking this as the arc. This is the arc, so it will cut like this. This portion was the extra path. These two are what? Radius, arc ka radius, right? These two are the radius of the arc. So now these two are equal. This is the extra path for second, and this is the extra path for first. So net extra path or the path difference would be this one. For central, you already know the path difference is 0. So minus mu minus 1 into T. This is for central. क्या होगा? Delta x is equal to 0. So dy by capital D minus mu minus 1 into T is equal to 0. You can find y. Okay, this is the position for central, y naught. What happens now? Central is shifted up. The first one would be shifted up, second would be shifted up. So now the position of nth bright would be n lambda capital D by small d plus this fixed value. Whole of the setup is shifted up. So this fixed value remains with everyone. So, okay, this is above O point. This is O point, above O point. Upper half में ये होगा. For the lower half, this thing should be negative. Getting my point? Okay, because agar if originally the fringe was formed here, now it would shift up. The distance is reduced on the lower side. So for lower side, this is upper side, and this would be n lambda capital D by small d minus d by mu, d by small d, mu minus 1 into t. This is for lower side. Same can be thought of for dark fringes, right? Fringe width would, what would happen to the fringe width? Fringe width is the distance between two fringes. Would it change? No, definitely not. It will not change. Is it okay? Can I erase this? लिख लो. अच्छा, one more thing. This distance through which the central moves up, the central fringe moves up through this distance. This distance is called fringe shift. Okay, this is called fringe shift. Okay, this is, I'm writing this because there are situations in which they use this name. Okay, I hope we should continue now. I hope you have written. Okay, so we don't have much time, and I want to finish everything in this topic. Is it okay? Okay, if time permits, I would bring some problems for all these, but today let's just finish the theory stuff. Is it okay? Can I erase this? Now, the pattern comes in anywhere where there are two coherent sources. Achha, I didn't discuss coherent sources, I'll just discuss it. Whenever there are two coherent sources, okay, interference will come in. Okay, there is some path difference as well, constant path difference. So it's not very difficult to create two coherent sources. So you must have studied this kind of topic. Condition for sustained interference. Okay, it's a NCERT topic. I'm just introducing it, I'm not explaining it. I'm explaining it, I won't be writing it, right? You already know quite a bit about it. So you need coherent sources for sustained interference. What are coherent sources? Now check. You have two hydrogen atoms. Okay. Are you sure that they are identical? Two hydrogen atoms, and they may not appear identical, but you already know that all hydrogen atoms would look identical. Okay, they all would have same faces, same color, complexion, everything, right? So they are identical, right? Exactly same. What happens now? We have so many orbits. Electron is in the innermost orbit. Okay, you give energy to both the hydrogen atoms in the form of electric discharge. Electric discharge पता है आपको? Okay, there was this cathode ray tube kind of thing. You reduce the you can say pressure or density, right? I was waiting for the right word. You pick the right, you reduce the density or pressure. What happens at one point of time? The gas pressure becomes very low. So cathode ray tubes, cathode rays pass through the tube. Okay, that is actually nothing but discharge. This kind of discharge happens during lightning as well. lightning जो होती है आसमान में, right? So by electric discharge you give energy to both of them at the same time. What would happen? They would instantly jump to higher level depending on the energy. Let's say you give energy so that they reach the third orbit. Okay, now what? You can never decide, you can always give the energy to them, excite them to the higher state. They would come back to their original state and release the energy in the form of light or UV rays, whatever, electromagnetic radiations, right? Okay. Now, you can always make them jump, you can always excite them according to your own wish, but they will not follow your wish while coming back. Marzi hoti hai. This guy comes down instantly, he waits, and a wait of 10 to the minus 8 meters, seconds, if he waits for only this much amount of time, what would happen? You can understand, in this much amount of time, the wave which is produced from here would travel through a distance of this Vt. Distance is equal to velocity into time, right? 3 meter. 3 meter is a large distance. हमारा setup ही इतना बड़ा नहीं होता. Our setup is like 1 meter, 2 meter, right? So the timing is an issue even when you are dealing with the most primary thing in the matter, atoms. Timing यहाँ भी match नहीं करा सकते ना. You can never match the timing whenever you have even 2 atoms. In a bulb there are billions of atoms. You can never match the timing. Okay. So now what happens? The light from this source and from this source can never match each other always. Okay, it may match at some point of time. It may happen that both of them are excited and they come back simultaneously. Light is produced simultaneously. At one point of time it may get delayed. At some other point of time it may get delayed. So there would always be a timing issue. Okay, and based on timing issue, how much delay happens, the distance traveled by the two waves would always matter. Okay, and in that distance there are wavelengths, and you remember that half wavelength difference can actually make or break your situation. So if there is timing difference of very small amount of time, isse crest nikla, just crest has come out of it, what would happen? Destructive. Okay, so for very primary kind of thing, atom, you cannot ever have timing match. For bigger, let's say you have 2 bulbs or 2 suns for that matter, one sun and you bring some another sun, and you try to interfere the light from them, you will have interference pattern obviously, but it would be changing very rapidly. Our eye cannot catch it. Why? Because of this timing issue, phi would keep changing. Do you remember phi depends on the distance, path difference? Okay, so since phi would keep changing, so at the same point, at one time there would be constructive, at some other time there would be destructive interference. So the pattern would be changing so rapidly, we would see only white light. Okay, no change actually, no difference in interference pattern. So you can never have sustained interference. Sustained means the stationary pattern is there. To achieve sustained interference, how do we approach? We actually divide one source into 2, which means we divide the light coming from a single source into 2 portions. Why? Because if there is some problem in the original source, the same problem comes in both the sources. And when we are considering path difference, so the difference, the common thing gets subtracted. Okay, if there is timing issue in the main source, let's say it affects first one, it affects the second one in the same manner, so difference would always be 0. Okay, is it okay? ठीक है, अगर distance का कुछ issue है, there is some issue, then the same issue would be with the first one as well as with the second one, right? So if you subtract, if you try to find the path difference would be because of the YDSC setup, not because of the timing issue, right? So you need coherent sources, which are the sources which have same frequency and same phase or constant phase difference. Okay, same frequency, only same frequency can never cause sustained interference. You need both. Second thing, to have good contrast, you need to have A1 equal to A2, so that dark fringe becomes totally dark. It would have a good contrast, right? And there are other things as well. The slits should be thin. Okay, why? Because if you consider thick slits, then thick slit can be considered as made up of many sources. Okay, so if you consider wide slits, it has many sources. They would interfere on their own. Apas mein bhi they would interfere. Okay, they would interfere together with each other. They would interfere with each other. So there would be mix and match of three patterns: pattern due to this, pattern due to this, then pattern due to the interference between these two big sources, right? So you need to keep it very thin. Is it okay? So I'll erase this one. This was a theoretical topic, but it is important to understand why do we need coherent sources. From 11th in sound there was this topic, coherent sources again. But in 11th also, from 11th people get troubled with this coherent sources. क्यों चाहिए होता है? Okay. The last topic we did was slab वाला ना. ठीक है. अब let's discuss interference due to thin films. Let's discuss the issue now. This is something which is not related to YDSC. Let's say this is a thin film, thickness T. A ray of light comes in. This is I, refractive index mu. Okay. This would happen. It bends, okay, this is R, and it comes out. This is angle I again, E is equal to I. But actually refraction is not 100%. Some portion of it gets reflected. And even refraction is not 100%. From here also some portion gets reflected. So it would come out. Even here also. So the thing is that multiple reflections happen. Okay. It is just that the first time is important to us. Why? The reason for that is, after first time, what happens? After first time, the intensity becomes too low to consider. Okay. So if you can just consider, this is the refracted ray 1, this is the reflected ray 1, this is reflected ray 2. They have small path difference. If you draw the wave fronts, they are like this. So obviously this portion would be extra. Are you sure? This would be extra too. Okay. All this distance would be extra. For wave 1, only this portion is extra. For wave 2, all of this is extra. Okay. Because of this, what happens? Interference would happen. And this kind of interference actually happens in our screen. We have a retina, a screen in our eyes called retina. So what happens is, our eye lens converges this on screen, on retina, and what happens? Interference pattern is observed. Have you seen this on water? Whenever there is some oil, it appears rainbowish, है ना? Violet, bluish. Why? The oil is colorless, water is colorless. Why are colors appearing when everything is transparent? It is because of interference of light. Incident white light comes in, and because of multiple reflections at different angles, different colors interfere constructively. At some angle red would interfere, at some angle blue would interfere. So it is just that, just because of interference we see rainbowish effect in oil. Okay, it's not in the sky, it's not in the color, in the oil itself. It's because of interference. So let's discuss this triangle. elaborate. Even for refracted rays, this kind of effect comes in. Okay, so for refracted also, let's first discuss for refracted actually. This is ray 1, ray 2. The thickness is T. The angle is R. Okay, JE asked earlier in some year, JE asked question on this actually, interference of thin films. When I is less, it's very easy to calculate, but when I is okay-ish type, when I is very less, actually you can calculate that these slant parts would be actually equal to T. Okay, the hypotenuse would be equal to T when I is very small. When I is appreciable, it's okay type, then you have to calculate everything. So this is T. Okay, now this is the path delta x1 and delta x2 is whole of this path, and you are traveling in refractive index mu. Okay, this angle is I, this angle is R. So if T is this angle, can I write this angle, this distance as T by cos theta, cos R basically? कुछ ऐसा ट्राइंगल है, this is R, this is T. Let's call it L. So can I write T as L sin L cos theta? T is actually base, so T is actually L cos theta. I can write L as T by cos theta, cos R basically should be there, and this again is T by cos R. So you can see that in these two triangles, the distance total in these two triangles, the extra distance traveled is how much? 2t cos R. 2t by cos R. Okay, this is delta x1. You need to calculate this one as well. Okay, time is over, right? I will continue with this one actually. Don't forget this. Okay. Tomorrow I will take up this because it will be a little lengthier actually. You need to fiddle around with a lot of angles. Okay. So let's continue on this tomorrow. Thank you.